In the last few videos, we've been looking at how alkenes can react with strong acid to give carbocations like this. Carbocations can then give us lots of different products, can give us haloalkanes, can give us alcohols or ethers, depending on what nucleophile is around to react with the carbocation. Right? So here I've got chloride, here I've got water, or here I've got some alcohol. So alkenes can give carbocations with strong acids. I want to talk about one more reaction that an alkene can do under strong acid conditions. And it kind of goes back to our SN1 and SN2 reactions, right? So if we only look at this carbocation intermediate, it might remind us of SN1 and E1, where we said that we would always get both reactions because it has the same rate determining step. So this is kind of like that. Just like these cations can give what kind of look like substitution products, I can also get an elimination product, right? So again, the second half of this reaction is just an E1 reaction. Methanol is acting as a weak base. It could be methanol, it could be water, it could be really whatever solvent is around to give us this essentially E1 product. Now, alkene to alkene, hard to memorize like that. But this is rearrangement. This is alkene rearrangement. So alkenes can rearrange under acidic conditions because that carbocation can eliminate to give either alkene. It's important to remember that when we see these carbocation intermediates, when we see any reactive intermediates, it kind of forgot where it came from. So in theory, no matter how I make this intermediate, I'm always going to get the same product distribution from it, okay? And so if it has a choice of going backwards to this alkene or forwards to this alkene, it's going to go to this blue one on the right because this is more substituted and therefore more stable, right? This alkene's got 1, 2, 3 non-hydrogen things on it. This one only has the 2 things. So because this alkene is more stable, these alkenes are rearranging to different alkenes via the carbocation. Notice that there's none of those fancy methyl shifts or hydride shifts. None of that is what I'm talking about here, right? This is simply a carbocation choosing among 2 different alkenes. So here are some more examples. This is 1,4-cyclohexadiene, 1, 2, 3, 4. And this is 1,3-cyclohexadiene. If I react 1,4 with some acid, or honestly, if I react 1,3 with acid, I can get this cationic intermediate. Now, from here, I can either take one of these green hydrogens or one of these hydrogens, including this red one that I just added. So if I just add, so here I'm adding this red hydrogen. If it just goes backwards, it just goes back to that. But if it takes a hydrogen from the other side, I get a different alkene. Which of these 2 alkenes, 1,4 or 1,3, is more stable? Well, this one is more stable because it is conjugated, right? Those double bonds are in conjugation with each other, which makes them more stable. They can share electrons across 4 atoms. Similar deal here, right? I've got 2 isomeric alkenes here. Which of them is more stable? The one that's more stable will be the one that has the lone pair in conjugation with that pi bond, right? When lone pairs are next to pi bonds like that, they are conjugated to each other. So this is going to be lower energy. So again, this thing, if it's formed, can go either way, but most of the time it's going to go to the lower energy intermediate. Another example, right? Isomeric alkenes can both access this cation, but if this cation can go either way, the lower energy, you can think about it like this, right? The lower energy product is going to be this one because my pi bond is conjugated to the benzene ring. One last example, again, isomeric alkenes. This cation can lose either a green hydrogen and go over here, or it can lose one of these red or white ones and go right back to where it started. If it loses this green one, now I get a new alkene that is conjugated to that CO. So this is going to be more stable pi conjugation, just like this was, just like all of these were. So the moral of the story is alkenes can rearrange under acidic conditions to give more stable alkenes. So you better be careful, because if you're having something that could rearrange to give you something more stable, it will do so.